Fine. So far we have discussed two basic thermodynamic processes, isothermal and isobaric. Okay. The next common thermodynamic process is an isochoric process. Now, what happens in an isochoric process? Isochoric means the volume of the gas is kept constant. It's not allowed to expand, it's not allowed to get compressed also. Okay, volume is kept constant. And it's very easy to understand how to carry out such a process. Just take a container whose volume does not change. Okay. It can exchange heat with the surroundings. Okay. But the volume should not change. Simple. So fixed piston. Don't allow the piston to move. It should not move outwards or inwards. So the gas cannot expand. It cannot get compressed also. So if you use a container of constant volume, you can carry out a constant volume process. Fine. So as usual, we'll have to draw the graphs for this process, then derive formulas, process specific formulas for delta W, delta U, delta Q. We'll do that quickly. Now we know PV is equal to nRT. And being an ideal gas, the gas will definitely have to obey this relation. Now the volume is kept constant. N and R are anyway constants. So you can say pressure is equal to nR by V multiplied with T. nR by V is a constant. So pressure is some constant multiplied with temperature. Therefore, pressure becomes proportional to temperature. Okay. So at constant volume, pressure of a gas is proportional to its temperature. And we are getting this from ideal gas equation. In an ideal gas equation, temperature must be in Kelvin. Okay. Absolute temperature. So here also the temperature has to be in Kelvins only. Then pressure will be proportional to temperature. That is okay. That is what happens in an isochoric process. Fine. Next thing we do is draw the graphs for such a process. Isochoric volume is kept constant. So suppose you want to draw the PV graph. The first graph we always draw is PV graph. Let's say you take pressure on the y-axis and volume on the x-axis. Volume is kept constant. So whatever you have on the x-axis is constant. If x is constant, that means the graph is a straight line parallel to y-axis. Simple. So at constant volume, pressure may increase or decrease depending on what you do with the gas. The graphs will look like this. Let's say this is carried out at fixed volume V1, you get a graph like this. If you carry it out at some other volume V2, you get a graph like this. Quite simple. Yeah. Next, pressure temperature graph. Now, volume is kept constant, but pressure and temperature are both allowed to vary. And we have just seen that if volume is constant from PV is equal to nRT, pressure becomes proportional to temperature. If Y is proportional to X, okay, little bit of mathematics as I said, the graph will be a straight line passing through the origin. P is equal to nR by V multiplied with T. We are taking pressure on the y-axis. So nR by V will be the proportionality constant. Temperature is being taken on the x-axis. So the proportionality constant between y and x is what you call as slope of the graph. Y is equal to mx. So the slope of the pressure temperature graph in an isochoric process, a process where volume remains constant, will be nR by V. So greater the volume, lesser the slope. Fine. The graph has to be a straight line passing through the origin. So it goes like this. We don't actually make it pass through the origin. It'll be like this. Let's say this is carried out at volume V1. Okay, at a fixed volume V1, if you see how pressure varies with temperature, let's say you got a graph like this. For the same gas, at another volume, if you carry out the process, the graph could be like this at a different volume V2. Now, what's the difference between these two graphs? The slope is different. First one has greater slope. Now we know that slope is nR by V. If pressure is on y-axis, temperature is on x-axis, then slope is nR by V. Greater the volume, smaller the slope. Okay. So the second graph, the one drawn for V2, has smaller slope. That means V2 must be greater volume. Okay, V1 must be lesser volume. So based on graphs, you should be able to tell which was carried out at under which conditions. Okay, such questions are quite common. So understand the approach. If you want to comment on which volume is greater, you need to know the relation between pressure and temperature, the formula or the equation between them. Based on that, you can tell how much is the slope or what is the formula for slope. And from the formula for slope, you can tell which one corresponds to greater volume. Okay, so this is the pressure temperature graph for an isochoric process. PV is equal to nRT, so pressure becomes proportional to temperature. Next, volume temperature graph. Quite simple. Volume remains constant, temperature varies. So depending on which axis you take volume on, you'll have to draw the graph. Let's take temperature on y-axis, volume on x-axis. If since volume is on x-axis and this is a constant volume process, it becomes x is equal to constant again. X is equal to constant represents a graph which is parallel to y-axis. Okay, straight line parallel to y-axis. So temperature is allowed to change. Volume is not allowed to change. So depending on the volume at which the process is carried out, you can get a graph like this. Simple. Okay. So we have drawn all three graphs for an isochoric process. Next thing to do is to derive expressions for delta U, delta W, delta Q and all. Okay. First, work done in an isochoric process. General formula for work done is integral P dV. Now, being an isochoric process, the volume is not allowed to increase or decrease. Now, if volume is not being allowed to increase or decrease, it means the effective displacement of the boundary is zero, boundary of the container. Gas exerts pressure, gas is exerting force, but displacement is not happening. Or on one side, positive displacement may be happening, on the other side, negative displacement must be happening so that the volume remains constant. So basically, there's no change in volume. So dV tends to zero. And since dV tends to zero, integral P dV will also become zero. Therefore, no work is done by the gas in an isochoric process. What does that mean? That means all the heat you supply gets stored as internal energy itself. None of it will be converted to work. Okay, that is what happens in an isochoric process. Okay, so delta W is zero. Always in an isochoric process, delta W has to be zero. Next, delta U, change in internal energy in an isochoric process. If you see, general formula for delta U is F by 2 nR delta T. So if you know the temperature change, you can substitute that and find out the change in internal energy. Now let us derive a process specific formula. Now we know PV is equal to nRT. And we also know that the change on the left hand side should be equal to change on the right hand side. Okay. This time volume is constant, pressure can change. So the left hand side becomes V delta P. Okay. It's like P final, V final minus P initial, V initial. V final, V initial are same. You take it common, you'll be left with V delta P is equal to right hand side becomes NR delta T. So NR delta T can be replaced with V delta P. You can substitute that here if you want. And the process specific formula becomes F by 2 multiplied with V multiplied with delta P. Okay. So as I said, you don't have to remember this process specific formula because for each process you'll have a different formula. You may get confused in the final exam, but you should know how to quickly derive it. Practice these derivations once. Okay. Not once, as many times as needed. You should be able to derive all these on your own. Okay. Then you can solve any question in thermodynamics easily. Okay. So that's how you find out change in internal energy in an isochoric process. Next is delta Q. We know delta Q is delta U plus delta W. Delta W is zero. In an isochoric process, it's always zero. Therefore, delta Q is equal to delta U itself. So you can write it as F by 2 NR delta T itself, or you can also write it as F by 2 as we just derived. V delta P. Okay. Now you see that we have a relation here between heat supplied and temperature change. If you have that relation, you can derive the molar specific heat of that process. Okay. Let us do that. Molar specific heat. And what kind of process is this? Isochoric process. So at constant volume, we call it as CV. Molar specific heat symbol is C. Since the volume is constant, we call it as CV. Now, C generally is delta Q by N delta T. Now, in this case, it becomes delta Q divided by N delta T, and it becomes equal to what? If you send N this side and delta T this side, what will you be left with? F by 2 multiplied with R. Therefore, CV of any gas is given by the formula F by 2 multiplied with R. Cp was F by 2 plus 1 multiplied with R. Cv is F by 2 multiplied with R. In fact, in chemistry, you must have derived or come across this equation. Cp minus Cv is equal to R. Okay, there is an elaborate derivation also for it. Uh, I don't know if you have done it or not. Okay. Now we got Cp as F by 2 plus 1 into R. This we derived yesterday. Cv, we are now seeing that it is F by 2 multiplied with R. Obviously, if you subtract these two, it becomes equal to R itself. Okay. So this way also you can prove that Cp minus Cv is equal to R for an ideal gas. Okay. Again, needless to say, Cv depends on the degrees of freedom. So it varies from gas to gas. So Cv for monoatomic gas will be 3R by 2 because monoatomic gas has 3 degrees of freedom. 3R by 2. Cv for a diatomic gas. Diatomic has 5 degrees of freedom, so 5R by 2. And for polyatomic nonlinear molecules, it will be 6 degrees of freedom, so 6R by 2, that is 3R. Okay. So it depends on gas, varies from gas to gas. And today we solved one problem, right, where we considered a mixture of gases, N1 moles of one type of gas having Cp1, N2 moles of another type of gas having Cp2, and we derived the effective molar specific heat. We can do the same with Cv also. Okay. And suppose something like that is given to you. N1 moles of one gas having Cv1 put together with N2 moles of another gas having Cv2, then the effective Cv becomes N1 Cv1 plus N2 Cv2 divided by N1 plus N2. So you can find out the effective molar specific heat of a combination also or a mixture of gases also. Fine. The next thing we talk about is bulk modulus of that process. Yusuf, can you tell me the general formula for bulk modulus? Like by definition, what is the basic formula for bulk modulus? Bulk modulus is generally volume stress by volume strain. And like we discussed in the last class, mathematically it's written like this. Okay. So it becomes minus V delta P by delta V. In thermodynamics, we take it as minus V dP by dV. And where do we get this from? We get this by differentiating the ideal gas equation. Okay. Now you don't have to do it actually because we are talking about an isochoric process. In an isochoric process, volume does not change. That means change in volume dV will be 0 or tending to 0. Okay. If dV tends to 0, the denominator tends to 0, then the bulk modulus in an isochoric process will be tending to infinity. What does that mean? See, as I said, or as we know, bulk modulus or any modulus of elasticity for that matter, Young's modulus or shear modulus or bulk modulus, they give you an idea of the rigidity of the system, okay, elasticity of the system. Greater the modulus of elasticity, more difficult it is to deform that system. Now, this is an isochoric process, means the volume is not changing at all. So you can say that the gas is incompressible. Okay. Even though you are increasing the pressure, the gas does not get compressed. What does that mean? It is not possible to deform the system. So it should be having infinite elasticity, infinite amount of elasticity. So bulk modulus will be tending to infinity in an isochoric process. Okay. So simple only, volume remains constant. Based on that, we discussed all the things that we do for any other, uh, any thermodynamic process. Okay, let's solve a few questions based on this isochoric process. First one. Okay, try this. In an isochoric process, what fraction of heat supplied gets stored as internal energy? Try this. I'll give you 2 minutes.
Say, so then
And,
we can substitute delta, we can move the Q to the side, delta U
huh,
divided by Q. And then we can substitute delta U by Q. So Q by Q is equal to 1.
that's all. Correct, correct. So basically what you are asked to calculate is delta U divided by delta Q. And as you rightly said, using the first law of thermodynamics, you can say that since it's an isochoric process, work done is zero. So all the heat supplied gets stored as internal energy itself. So what fraction gets stored as internal energy? 1. Okay, 100%. What fraction gets stored to work, converted to work? The answer will be 0. Okay, fine. Let's try another question based on a graph. Okay, let's say volume on the x-axis and there's pressure on the y-axis. It's an isochoric process. So volume will remain constant. Assume the volume is V naught and pressure can change. Let's say the pressure increases from an initial value P naught to a final value, say 3 P naught. Okay. You can see the direction in which the process is carried out. And see, the graph is a straight line parallel to y-axis. So there will be no area between the graph and volume axis at all. See, had the graph been like this, there would have been some area under it. But since the graph is a vertical straight line, you won't have any area between the graph and the horizontal axis. So since there's no area, you can say work done is 0. Okay, we know that anyway. In an isochoric process, work done is 0. So suppose there are n number of moles, n is given to you, and degrees of freedom F is also given to you. And this is the process. Pressure is increased from P naught to 3 V naught. Derive an expression for heat supplied in this step. Try. Tell me what different ways are there to calculate delta Q? One is to use the first law of thermodynamics. Another way is to write NC delta T. Okay. Like you have very few formulas in thermodynamics. You just have to think of which is the appropriate one to be used in a particular situation. Okay. You can do it both ways actually. Now see clearly this is an isochoric process. Work done is 0. So whatever is the change in internal energy, the same will be the heat supplied. Okay. And for internal energy, we have a general formula, F by 2 nr delta T. And in an isochoric process, nr delta T changes to V delta P. So if temperature had been given, you could have used nr delta T directly, but the graph is in terms of pressure and volume, so we use V delta P. Simple. So F by 2 times, what is the volume at which it is carried out? V naught. And what's the pressure change that is happening? P naught to 3 P naught. So the change in pressure is 2 P naught. The twos cancel. The answer is F P naught V naught. That is the change in internal energy. Same will be the heat supplied. Okay. Suppose you used NC delta T. N, you have to use the C value, molar specific heat, for this particular process. Molar specific heat at constant volume we just derived is F by 2 multiplied with R. That will have to be used, multiplied with delta T. You get the same answer, F by 2 nr delta T, which can be written as V delta P, and it will be equal to F times P naught V naught. Is this clear?
Yes, sir. Yes, sir.
Okay, fine. Right. So, okay, that is enough about isochoric process. So we discussed isothermal, isobaric, and isochoric. Tomorrow's class will discuss another thermodynamic process called adiabatic process. Okay. And if time permits, we will talk about something called a general polytropic process also. But adiabatic process, there will be more derivations involved. So a slightly tricky process, you can say. Like in these three processes, isothermal, isobaric, isochoric, one of the thermodynamic state variables was kept constant, temperature or pressure or volume. In an adiabatic process, none of them will be constant. Okay, so that is what makes it slightly tricky. We'll discuss that in tomorrow's class. Okay, thank you.